Good morning, student. Good morning to all of you. Today we are going to discuss a topic that is Ampere's circuital law. What is Ampere's circuital law? This is another method or alternate method to find the magnitude of magnetic field around the current carrying wire. The basic method is Biot-Savart law, but it is an alternate method to find the magnitude of magnetic field around the current carrying wire. So we can write here that this one alternate method, okay. To find B, okay. The basic method is Biot-Savart, okay. According to this method, we see here, suppose there is a current which is inward. The cross indicates the current which is inward. Suppose we can assume that there is a current I1 which is inward to the board, and there is another current which is I2 which is outward to the board, okay. Then if you want to find the magnitude of magnetic field at a point P, then we have to assume an Ampere's loop. What is Ampere's loop? The Ampere's loop is a curved line which is passing through the point P, from where you want to find the magnitude of magnetic field. Passing this point, you draw a curved line, and this loop is called Ampere's loop, okay. This one Ampere's loop, okay. And we have to consider here that the loop should be in symmetrical shape, okay. The loops should be symmetrical shape, okay. This is called having a length, some length of curved line. This special name of this loop is called Ampere's loop, and we have to choose an arbitrary direction that is called direction of loop. We choose here clockwise direction. We choose here in clockwise direction. So the direction of this loop is here clockwise direction, and according to Ampere's circuital law, we have to find the direction of current, that is positive or negative. Then we curl our right hand 4 fingers in the direction of loop, and your thumb will give the positive direction of current, and opposite to the direction of thumb will give the negative direction of current. So here we curl our 4 fingers in the direction of loop. So curl your 4 fingers in the direction of loop. Direction of loop. Then your thumb will give positive direction. Positive direction of positive I, okay. You can write a positive I, and opposite thumb, that is opposite thumb. Opposite thumb will give that negative value of I, okay. Negative value of I, okay. So here if you curl our 4 fingers, then you see that the I1 here positive, here I1 positive, and definitely the I2 will becomes negative, okay. And according to this law, that the B dot dl, that is the integral length of this loop. Suppose there is a length, that is elemental length. We have to choose an elemental length which is in the direction of loop also. This one we cut an element having a length dl which also in the direction of loop. This one we can cut many elemental length dl which is in the direction of loop, okay. Here dl which is in the direction of loop. So the integral length, that is with B is the magnitude of magnetic field at a point P or at on the loop, the magnitude of magnetic field on the loop. So the B dot dl is equal to mu naught into I inside, okay, I inside, B dot dl into mu naught into I inside. This one the law Ampere's circuital law. Okay. And where is the direction of dl is, that is tangential to the that is in the direction of loop. Okay. And for the B, what is B here, that is the magnitude of magnetic field, there is some rule, that is some criteria, for B, that is some condition for magnitude of magnetic field, that is the B should be, the first criteria that the B should be tangential to length. The B should be tangential to length or uniform or constant. Okay, or constant and non-zero. For B, there is a condition, that is the B should be tangential, means what? The B should be in the direction of here length. Tangential means in the direction of length or opposite to the direction of length. Here the B is opposite to the direction of length, and here in the direction of length. If here in the direction of length, then theta becomes 0 here. Here theta becomes 0. B dot dl, here theta becomes 0. But here theta becomes how much? 180 degree. So here B dot dl becomes how much? B dot dl, that is becomes B dl cos 0 1 times and 1 times B dl cos 180 degree. Here the cos 0 becomes 1 and here cos minus 1, and you get some value of B dl. And the second condition is that the B should be perpendicular to length. The B should be perpendicular to length. B should be perpendicular to length. If the B is like that, length is in the direction of tangent, then B should be like that, then you get theta equal to 90 degree. Here theta equal to 90 degree means here the theta becomes how much? 90 degree. So integration of B dl dot dl becomes a B dl cos 90 degree, and you know that cos 90 becomes 0. So there B dl becomes 0. And the third condition is that B is vanishes, means there is no any B is appears here. So the B dl becomes 0. Okay. This one the condition of B. Okay. And there is a note about this Ampere's circuital law. There is a note that if suppose this one Ampere's loop, suppose this one Ampere's loop, and inside the loop there is a two current, that is I1 and here I2. Okay, I1 and I2 here, and there is also some current which is outwards out of this loop. Okay, that is boundary of the loop, outwards of the boundary of the loop. That is suppose here I3 that is inward, and here I4 that is outward direction of electric current. Then what about the magnitude of magnetic field at a point P? Here if you want to find the magnitude of magnetic field at a point P, this magnetic field, the B is due to whole current, okay, we can write here the B is due to whole current present around the point. Means if you want to find the magnitude of magnetic field here a point P, that is B, that B is due to the whole current, either it is inward to the loop or outward to the loop around the point, either it is inward or outward, in or out of the boundary. Okay, in or out of Ampere's loop. This one, note that here the magnitude of magnetic field is due to the whole current present around that point, that is the current which is in or out of the Ampere's loop. The total magnitude of magnetic field is due to the total current present near the point. But in formula we will take only, that is I inside, but in formula we will take only, that is I inside, here I inside, that is we will take only I1 minus I2, that is here I inside, that is I1 plus and I2 minus, if the direction of loop is in that clockwise direction. Okay, that is inside here we will take in formula I1 minus I2 only, but the magnitude of magnetic field is due to the total current present near that point, either it is inward to the Ampere's loop or outward to the Ampere's loop. Okay, I think you are able to follow me. Again here the I1 becomes positive and I2 becomes negative. So I inside, that is I inside here becomes how much? I1 minus I2. Okay, I is positive and I2 is negative. Okay, and there is an example to find example that if there is a wire is having a current I and you want to find the magnitude of magnetic field at a point P. The wire is having infinite length, then you want to find the magnitude of magnetic field at a point A, at a point P, at a distance A from this wire. Then we use here Ampere's circuital law to find the magnitude of magnetic field at a point P. Then we draw a Ampere's loop which is passing the point P. Okay, and if you take the top view of this loop, here we get a circle, okay, having a radius A, and inside the circle at a point P we have to find the magnitude of magnetic field, and inside the circle the current is passing outward, that is passing outward. So we draw here dot, the current is passing outward. Okay, so here the current is I, and at a distance A, at a point P we have to find the magnitude of magnetic field. Then we choose here where is the direction of magnetic field, we will consider here, because in this formula integration B dot dl, there is a the B should be, that is constant, the B should be constant and tangential. So we use your right hand thumb rule to find the direction of B. We know that right hand thumb rule, we place our thumb in the direction of current and our 4 curling fingers will give the direction of magnetic field. So here we see that the direction of magnetic field be in how we place our thumb in the direction of current. The current is outward and we curl our 4 fingers in the direction of the 4 curling fingers will give the direction of magnetic field. So here the magnetic field, here the direction of magnetic field is anti-clockwise, and we choose here the direction of element, that is dl element, also in this direction, because we have we can choose the direction of dl in any direction, arbitrary direction. So we choose here in the direction of B. So this one the direction of dl, and B also the same direction. Okay, so the theta becomes how much here? Theta becomes 0 degree. So we apply formula B dot dl equal to mu naught I inside. Okay, mu naught I inside. So here B dl cos 0 degree, and we know that cos 0 degree equal to 1. Okay, and this one mu naught I inside. Here I inside means the current is I, so we put here I. Okay, put here I. Okay, and this value becomes 1, this B will come out because B is constant here at a distance A, the B is constant, and tangential will come out, and the dl is for whole circle. Okay, this one for whole circle, and equal to mu naught into I. As we integrate, we get dl we get 2 pi r, the circumference of the circle, that is 2 pi a. Here distance is a, so here, and mu naught into I. Okay, and as you calculate the B from here, that is mu naught into I divided by 2 pi a. 2 pi a. We see here, we have already find the magnitude of magnetic field due to this infinite length of current carrying wire by Biot-Savart law, by applying the rule Biot-Savart law. But the same value we can get by using the Ampere circuital law. This one by applying the rule of Ampere circuital law. This one Ampere's circuital law. I think you are able to follow me. Thank you very much.